Alright guys, so do me a favor and put those away for the time being. You can still, now trust me, just like on quizzes, I hate to give back corrections and say, your grade is still this. You got no points back because they're all wrong. And I've had to do that several times. It doesn't make any sense. You can go to the tutors to get help. You can come see me and say, I'm not turning this in yet, Jeff. Just tell me if it looks okay. Tell me what I got to still work on. Right? If you don't get those points back, it makes no sense. Test corrections kick ass because tests are relatively heavy weighted. So test corrections are the quickest way to boost your grade. It's crazy.
Oh yeah.
So really, yeah. So focus on that. Okay. So any other questions before we get back into 3-4? Everybody else okay? Okay. You're bummed out or you're happy? At least you know what the hell happened. Okay. All right. So we've talked about the Z-score already, obviously. Can somebody help me out? I've already said this, but this is in section 3-4. If I know the mean is something and I know the standard deviation is something, how do I find the max and min usual value? Or sometimes also called expected values. So if I go from the mean out, and we've talked about this before, if I take 2 steps out, 2 standard deviations out in a normal distribution, how much is left outside?
3% or 5%.
Yeah. So how much is in there?
95.
95%, good. So how much is outside?
5.
5%. So right now, we're going to officially declare that anything that has a probability that's in an area with a probability, so if I had somebody who is this tall, whose z-score was above 2, I'm going to say they're unusually tall. Because only 5% of the people are like that far away from the mean in that area. You guys semi with me here? Later in the course, we're going to refine that, and we're going to allow a definition of unusual to change based on the circumstances we're in. Right? So if I'm at a nuclear reactor, and I don't do something until I get into unusual territory, I might define my unusual territory to be a little bit further in, just to be on the safe side. You guys see what I'm saying? Maybe I want to know well in advance if something's getting too hot. I don't want to wait until it's like here. You know, it's like, I'm really unusual, you're going to die. Oh, well, shit. You guys kind of with me? But right now, officially, it's 5%, which means if I had a mean of 11.2 and a standard deviation of 1.97, can you take a second to figure out what the minimum and maximum usual values are? Try something. I will never see what you're about to try, so you might as well try something.
All right.
Uh-oh.
This would be 15.14.
So what do you do mathematically to get to the minimum usual value?
Minus 1.97 times.
Yeah, you take the mean minus 2 standard deviations, right? You go down 2 steps to get to the lowest expected. And anything below that, if it's height again, it'd be unusually short. You take a double take. Well, I don't see that every day. I don't see somebody that short, or I don't see somebody that tall. So this would be 11.2 minus 2 steps. So start the mean and take 2 steps down. And where do you end up?
7.26.
26, okay. And what about the max? You just take 2 steps up. 11.2 plus twice this.
15.14.
15.14.
Thank you. Cool. Does that make sense? That question, so very often in this book, in different chapters, they'll ask you this question. You will have different ways to calculate the mean and the standard deviation, but you always do the same thing there to figure out the max and min usual values. Okay. How are we doing so far? Relatively okay? All right. Good, good, good. All right. So let's get back into the last thing we were doing, the percentile stuff. We started getting into that a little bit. And I don't know if you remember, but I had like 10 numbers up here. Make up some real quick here. One, 2, 3, 4, 5, 6, 8, 9, 10. And we went through a little bit of a process to figure out. And it's to be expected that your answers were wrong at first because you're not sure exactly how to look at this. But it's a lot like the median. Right? So it's actually, the median is a specific example of a percentile. So if a percentile means that that percent is below that value, right? All right, that sounds weird. Let's give a concrete example. So if your SAT, the NS and theirs, if your SAT was in the 90th percentile, and that's just way too many letters for math people, so we call that P90. There we go. Of course, that sounds like a workout routine. Join the P90 revolution. If your SAT was in the 90th percentile, then that means what? What does that mean? Does that mean you made an A minus?
90% of the people.
90% of the people that took that same test on the same day scored below you. That's what it means. That's all a percentile can mean. So if your SAT was in the 90th percentile, then 90% of the students, of the people who took that same SAT, that same test, scored below you. That's what that means. And that makes it fair. Because every time they change the test, they could arbitrarily make it harder or easier. So if they make it harder, everybody scores lower, but you're still in the relative same position to everybody else. You guys with me? That's why having a relative measurement like this, which is the whole point of this chapter, this section, is more fair. Okay. So let's get back into the specifics of how do you calculate this thing then. God, my writing is getting even worse. I don't know how you guys do it. You have to listen to what I say. All right, you guys got this here?
No.
No.
What's under 90%?
90% right here?
Under that.
Oh,
P90.
P90? 90% of the people who took that same test scored below you. Yeah, so that's what that means if you're in the 98th percentile.
So if you're in the 70th percentile.
All right. All right. So let's look back up here. If I wanted to calculate what P80 was, I don't know if you guys remember where we left off with this. Let's see what makes sense. And some of the suggestions were the 8th one or the 9th one. Right? The 8th one's no good because it only has 7 below it. It's supposed to have 80% below it, right? And the 9th one's no good because it only has 10% above it. It's supposed to have 20% above it, so it's right there. So it's just like the median. You have to, if you have 4 things, you have to average the 2 in the middle. So here's the 2 steps. The 2-step process. The first step is, where's the answer? And the second step is, go get the damn answer. Right? So the first step is, now think about it. I got, however long my list is, where should I go to find the 80th percentile? What percentage of the people should I pass? 80%, right? If these are scores on some tests, I want to pass 80% of them around, and then we got to figure out how to adjust it so it gets in the right place. So the first step totally makes sense. take 80% of however long your list is. So it'll be 80% of 10. 0.8 times 10. I love the fact that less and less people understand what the word of means. It used to be a normal, everybody knew what of meant. Now I notice less and less people coming out of high school knows what of means. And it's not a Clinton moment. Depends on the difference. No, it's what does of mean in math? I already told you, it's times. 1/5 of 12. I take 1/5 times 12. Some percentage of something. Of means multiply, not divide. So what is 0.8 times 10? That's crazy. And if it comes out to a whole number, I think we got this far last time, but it was pretty quick at the end of class. If it comes out to a whole number, you average that one with the next one. If it comes out to anything else, you round up to the next one. So for this example, it came out to a whole number, so the answer is going to be in between the 8th and 9th number. So I go to average the 8th and the 9th number. So what's the 8th number? 52. What's the 9th number? 58. It's great. And then if I average those out, I get 55. Thank you. And be really, really careful. I saw some calculator errors. You guys had it set up correctly, but you got to tell the poor calculator what the top is. Calculator doesn't have eyeballs yet, right? Maybe the TI 3000 will. Right? And that, of course, is when they'll be like actually looking like Arnold Schwarzenegger. That'd be your problem. Sorry. So, do you see what I mean, though? Somebody would often circle that and stop and say the answer is 8. I'm like, how would that, 8's here. How would that be the 80th percentile? So, where's the answer? And then go get the answer. So, this first step just tells you where the answer is. You have to then go get it.
So, what if it was 7 point?
Beautiful. Let's do it. All right. You guys have this by now. If you don't, let's do that. So let's say I want to get P80. Let's say I want to get P63. So go ahead and do it for this set of data. I want you to realize there's only 10 data points up here. So it doesn't make the most perfect sense, but we still follow the process. So you do the two-step process here.
All right.
Oh boy. That's 89. Oh, it's a map.
You don't have to average it because if it's a whole number, you average that. If it's a decimal, you round up. Right? So it's just the one. I'm pretty sure. Well, I'm pretty sure it's just.
It would be float. It would say something about float. Yeah. All right. Good. Thank God Google exists. What's the first step here, guys?
0.63 times 10.
All right, Jababa. 62% of 10. 6.3. It's not a whole number, so you just round up to 7. Seventh number is your answer. What is the seventh number? 51. 51? Sure. Okay. So what would P64 be? Same. Now, don't discount the idea. There's only 10 freaking data points. So, of course, there's going to be a lot of repeats. Right? So the larger set of data you have, the more specific sense some of this makes. For 10 data points, of course you're going to have a lot of repeats. P63 is the same thing as P64 is the same thing as P64. Of course it is, because there's not that many to choose from in the first place. You don't have as much good resolution, right? I love my grammar. Much good. Good thing I'm in this department and not English. Okay. So how are we feeling about that? That's actually, if you let it be, I mean, that's a breath of fresh air after having to go crazy with the tables and the standard deviation and shit. Right, which some of you guys still have to redo, but that's all right. All right. Any questions on that? Yes?
So whole number, then you have to find the average. But
Good.
if it's not a whole number.
Anything else, you round up. So we would have gotten 6.00002. I would have rounded up to 7. Yeah. Yeah.
So in the second example, the answer of P63 is a 7. But why in the first example P80 is 6.8?
Again, the first example, the first step came out to 8. That's a whole number. If it comes out to a whole number, you average that one and the next one. That's the process. And think about it. Now go with me. What would a median say about 5 numbers? Where's the median number? Which one? Yeah. Oh, this one. I'm not that angry at you guys, so there's no reason. Some classes, yeah. Not this semester yet. So that would be the answer, right? But what's half of 5? 2.5. So there's a 2 and a fifth number. No. You round it up to the next one. You say the third number, right? So what about 4 numbers? What's half of 4? 2. Is 2 the right one? No, it's that averaged with the next one, right? So just don't forget that median is a specific example of a percentile. In fact, the median is the what percentile? 50th percentile. There you go. So the median is just specifically the P50. So the process you use to find the median is actually the same kind of process they use to find any percentile. Whole number, you average it with the next. Anything else, you round it up and take that number. Beautiful. Yeah. No. Why? 70th percentile, P70 would be 70% of 10, which is 7. So I'd average the 7th and 8th, right? If it comes out to a whole number, you average it with the next one up. Yep. Anything else, you round it to the next one. Yeah.
So with the 63rd percentile, since it's 51, is 51 included, or is it everything below 51?
So if you got a 51 on this test or quiz or whatever, you would be in the, what am I trying to say? What was it? The 63rd percentile. So 63% roughly. It's a small set of data, so it would have scored below you. All right. Maybe. Okay, cool. Sort of, kind of, okay. Okay. So let's build up to what a box and whisker plot is. One of my favoriteest things in the world. You see this kind of thing in science a lot. You see this kind of thing if you look in the Princeton Guide of Colleges. You'll actually see like the middle 50% SAT scores and stuff like that. I actually had to calculate that for my old college. So what the hell's that got to do with anything, Jeff? I don't know. The box and whisker plot is made from 5 numbers. And they're called a 5-number summary. So if I have a basketball game, how do I break up that basketball game? Into quarters. I love it. So we do the same thing with data. So it's my set of numbers that will summarize the data. I want to know what the highest and the lowest were, right? The low and the high. But I also want to know what the quarters are. So I'm going to call it Q1, but we know that's what percentile? P25. So don't freak out. Q1 just means P25. So amazing enough, the next one is, oh, right, P50, which is also known as the median. And then, of course, Q3, which is P75. Kick ass. I erased my data. Oh, suck. So, let's make some more data, some more interesting data, more than 10. You ready? Here we go. It's going to be exciting. Now, I notice, what was it about the data that I did earlier that was nice? I kind of gave it to you in a nice way. It was in order already. So obviously, if it's not in order yet, you got to do that first, or else none of this makes any sense. You can just make P85 whatever the hell you want it to be. Let me get that one. Yay. That's not how you sound, but. So I'm going to give it to you in order, just to cut to the chase here. Maybe is how you sound. One of my favorite Monty Python characters. Ooh. What is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16. That's good. All right, I can live with that. No, 2 more. Haha. All right. There's 18 data points up there. That's important. So I want to find these 5 things. So as soon as you get those written down, try to find these 5 things. Here, I'll do 40% of the work for you. Yeah, I mean, who else does that for people? You're a dork, Jeff. Yes. Jeff's figuring that out. Call me over if you need some help. Oh, so the equation is like A over N. Sure. So sure. We're using the equation, to be honest. So I don't like the equation because it actually makes it harder than it needs to be. But if it makes more sense to you, that's fine. Yeah. Yes. Okay. If you count it in there, I just got to count it to the middle. Yeah, so if it's a small enough data set, you can just find the median like almost. Just count it to the middle. All right, let's make sure we're doing this right. What about Q1? What is 25% of 18? 4.5. So what do? Yeah, you take the 5th number. And what's the 5th number?
105.
105. That's crazy. So Q1 is 105. Now, notice how I didn't put any room for Q3 up here. And that's on purpose. If the... Well, let's see if you guys kind of get this. Well, maybe not. We'll do it and then I'll show you a shortcut. So here's 105. What about P50, which is the median? So you can find the median like always, you just kind of count into the middle. But let's try it this way real quick. Half of 18 is 9. So do I just take the 9th number? No, I do what? Yeah, 9th and 10th. The 9th and 10th ones are?
180.
Good. So what's the average of those? 175.5? All right, so that's 175.5. And then, now, who did this here? Let's see, real quick. What would 75% of 18 be?
13.5.
So you round it up to the 14th one, right? And then you start counting in.
212.
212. But notice, didn't we have to count 5 in from the top to get to Q1? So a shortcut for Q3 is count 5 in from the bottom, because they got to be symmetric, right? Boogie woogie. So 1, 2, 3, 4, 5. Hey, all right, 12. You guys see what I'm saying?
I don't only work with 3 then.
No, it'll work always.
Wait, say that again?
For Q2,
Q2?
Man, no, I got
having
that.
5 from Q1.
Oh, yeah. Once you kind of figure out how far they're all spread out, yeah, it'll actually work that way too. I like it. So if you're at 105, 1, 2, 3, 4, 5, you got to realize, though, it has to be in the middle. So another way to do this problem is to cut that in half and then cut the halves in half. Right? But this is just a little more, you can sink your teeth into this. You can see it happening better. So here's how you make, was that hard? Was that difficult? And to be honest, if you put those data points into your list 1, and you did 1 var stacks, everything I just said shouldn't have been Greek, right? Everybody knows what I'm talking about? So you can see your X bar. If you hit the down button, because there's more stuff it tells you, the last 5 things it tells you is this. It gives you the 5-number summary up there. That's not good enough for work, right? Don't just tell me the buttons you hit. But it's nice to check your work, right? You can check your work doing it. To make a box and whisker. This is the official name of this thing. It's not my name for this thing.
Wait.
How are we doing? Here's how beautiful this is. I want to make a scale, a number line that has all these points have a place to go. So where should I start, and maybe by how much should I step? Can somebody help make a scale that'll catch all these? So maybe I could start, if I start at 50 maybe, and just put 49 right below it. You with me? 49 is my first one, I just put it right below it. And then I got to make it up to 300. So maybe I could step by 50s, yeah. So 50, 100, 150, 200, 250, 300. There you go. Not too bad. So this idea of making a scale that doesn't necessarily have your data point numbers in there, but has a place for all your data values to go. And then here's the really cool thing. You ready? All right. And then, you know, it's not like monster cool, but still. You put a little line where the 49 is. That's Q1. You just put 5 little lines for your 5-number summary. So 105 is right there. 175 is right in the middle of those two, just about. 212 is closer to 200, and 301 is just on the outside of 300. All right, so just do that for right now. I mean, do you guys see what I'm doing? I mean, I'm not really putting little points. I'm just putting lines above where these are, and you'll see why here in a minute. Yes, sir.
Why don't you just put like Q2 in the middle? Like, why don't you write 175 there?
Oh, sure. You could build it out from the middle if you want to do that. Yeah, sure. You can make it as long as your scale has a place for everything to go. I'm happy.
All right.
I like it. Now here's the next thing you do. So here's the box part of the box and whisker. You box off the middle 3 like that. All right. What's that?
Why you did that?
Because. And then for the whiskers, you do this. Here's why. Here's why. Can somebody tell me what percentage will always be in that middle box? I don't care what your data is. Remind me, what was this? What is that specifically, physically? Q3, right? That's Q3. What was this one?
Q2.
No, that's Q2. Q1. Stay with me now. How much is below Q3? By definition, the third quarter has how much below it? 75%. How much below Q1?
25.
How much is in the middle? 50. So that's the middle 50%. So you see this all the time in data analysis, especially with, like I said, colleges always have to report the middle 50% SAT score spread. So what's Q1 to Q3 for their students currently? What was their scores? Because then if you do that, you could have one college is like this, and another college is like this. You with me? And then you got a college, what college is this? Well, maybe Harvard or something, right? And this, you know, this would be... There you go. I didn't want to say it, but yeah, that's basically for breathing. We'll take you. Harvard, they'll be a little bit more choosy, right? And this would be just some other college somewhere. But if you put a bunch of box-and-whisker plots next to each other at the same scale, you can compare them to each other very quickly. It's a quick visual comparison that you can make. And it's a relatively quick data analysis that you can do. You guys semi with me here? All right. So again, the question of why is just because some point in history we decided that this is a decent way to display certain data sets, right? The middle 50% is the middle chunk. It's like your heartland, right? You want to say heartland, was folks. So the heartland of whatever you're talking about. So that's just a quick visualization of where they are, and then this gives you an idea of the spread of the data. It's not standard deviation, but it does give you an idea of how spread out your data is. Okay, so who up here would have the largest standard deviation, obviously? The middle one, yeah. So now who has the largest standard deviation? Still the middle one, right? And even if I did this, now this would be remarkably weird. Right? This is the TIE fighters who really been pimped out. Sorry. So this would still have a smaller standard deviation than this, because a lot more of the data, 50% of the data is in there. It's just that they accepted one guy who put his name on the test, and that's it. And then they got the guy that noticed there was a mistake on the test, so he actually got 100 extra points for that. And that's why the range is huge, but the standard deviation would be small, because 50% of the data is like right there. Okay, maybe you guys are with me. Now, how important is it to really get what I just said and be able to do it? Not extra important. But that's just another powerful thing about these. They're relatively quick to make, and you can see a lot of information about the data sets. Okay. All right. Maybe let that be semi-easy. That's not that bad. The math involved there is easy. Draw lines over a number line. You wish your math classes were all like that. All right. So that's section 3.4. So they talk about find number summary and box plots starting on page 118 if you want to look at those. So we are going to get a little bit into chapter 4. Okay. So any questions before we move on? Yes?
For work on the homework, would the crossing out count, or do you want to do that?
Yes. I want to see this. Cool. Just the middle 3.
Oh.
You put 1, 2, 3, 4, 5 lines, and then you box the middle 3.
Oh.
Yeah, it's beautiful. It tells you a ton of stuff, and it's just like connecting lines to make it. It's like, oh, whoa. Very simple to make, very powerful to look at. All right. So, I don't know if you guys remember, we talked about like the birthday thing. We did that on the first day. And we had several people that, we had the 2 people that were only there that first day. And some of you guys might be like, oh, I think Jeff just brought them in there. But no, I don't know what happened to them. But they were both born on the same day. Right? And then we had some other people that were born on the same day. You guys remember this? So it's always a higher probability than you expect it to be. Because you're always thinking about it from your own perspective. You're like, nobody else has my birthday. No way. What I want to do is one semester I want to say, write a number from 1 to 365. And then see if anybody wrote the same number down. And do you see how that should be somewhat equivalent, right? Does anybody see how that should be equivalent?
Yeah.
Because it's 365. And I want to see if anybody writes the same number down. That would be the same thing as 2 people having the same birthday, right? Okay, good. I like it. So maybe I'll do that someday. I want to go back and talk a little bit about the Monty the Monty Hall problem, the goats behind the doors, right? Just for a second, I don't want to talk too much about it, but just to show you how our brains are just not hardwired for this kind of stuff, which doesn't mean that we're not supposed to do it. It just means that we have to be extra careful when we're doing probability stuff. We can't just say, oh, it's going to be this. So the whole thing with the Monty Hall problem. I don't know if I did explain this a little bit, but I'm not sure I brought all of you guys over. So the idea with this is what it used to be is at the end of the show, you take the person that won the most or whatever, and they have the option to trade in their stuff for a chance to do this. And what this is behind two of these there's a goat, and behind one of them there's like a new car or something, right? You guys with me? Something more than a coffee maker, something big, boat, trip. So if you just pick one, what's the chance that you pick the prize? You pick the big, good prize. Yeah, so the probability of picking the prize on the first go and I don't know if any of you guys read, probably not, the parade section in the Sunday newspaper. Do you know they still make newspapers? And there's the parade section. Anybody by chance? No? Scheiße. It's not a big deal. But I just want to say that they spent like all this time explaining this. And I'm going to desperately try to show you it shouldn't take much at all to explain this at all. The idea that we've already got the answer up here. If there's a 1/3 chance that you pick the prize, so somebody pick a door. 2. All right. So you pick 2. All right. So there's a 1/3 chance you're right. And then I open door number 3. I open it up and I show you there's a little goat in there. Don't worry about the goat. He's going to be okay. I can't make a goat head. He's angry because he looks horrible. So I show you door number 3. I show you there's a goat. So most people think, well, now there's a 50-50 chance. But it can't change. It can't. Just because I showed you there's a goat there, it does not change the probability you pick the prize. It can't change it. There is a 1/3 chance you pick the prize. I don't care if I open that door. There's a 1/3 chance. Yes, ma'am?
So is it luck then?
If there's a 1/3 chance, and let's talk about what that really means. I like this. Maybe I can go further with this than I was originally thinking. What the hell does 1/3 chance mean? What does it mean? I love my little brother. My little brother would say, have I talked to you about my little brother yet? I always bring him up. I still tell him I bring him up. And he says to me, Jeff, you still teach that probability stuff? I'm like, yeah. He says, it's all shit, man. It's either going to happen or it ain't. It's going to rain or it's not. I'll see if it rains. I'm like, Jim, this is like 20 years ago. I said, Jim, don't become a doctor. Because I don't want to be going in, Doc, what's my chances? 50-50? No, don't be doing that shit to me. You with me? So it's not, you'll make it or you won't. That's life. All right. Screw you. You guys with me? So there are probabilities. Unfortunately, people think probabilities can do more than they can. And people that try to play the stock market or the lotteries and they say, which numbers haven't been chosen in a long time, they're going to definitely know. It's bullshit. You can't see, we as humans, we think, oh, there's got to be something magic with this. We should be able to do this. Use it. No, screw it. No. But there's still, if a doctor tells me I have a 99% chance of surviving the surgery I'm about to go in, I feel a lot better than if he says, 50-50. You with me? So it means something. If they say there's a 20% chance of rain today, that's a little bit different, then that means 20% of the time with the conditions we're in, it would rain. Now, let's go back. What does that really, really mean, though? If I flip a coin, what's the chances I get a head? 50%. But if I flip it once, it doesn't make a damn bit of sense, does it? Do I get half a head? What does that mean? Right? So what does it really mean? What does a 1/3 probability mean? We're not done with this yet, but I love that you asked the question because this is a huge piece of what we got to talk about. What the hell does it mean? So what it means is this. You ready? There's something called the law of large numbers. And this is not my name. I did not name this. The law of large numbers. It's a law. You must obey it. So what it says is, in the long run, our observations must match what we predict will happen. So if we do this, and they did this on one of my favorite shows, they did this on Mythbusters. They actually set up the whole thing and they did the experiment. They actually did this and they ran it and they actually came out close to this number. For the people that, if you switch, you'll win 1/3 of the time. If you don't switch, you win 1/3. If you do switch, you'll win 2/3 of the time. Of course you will. We'll talk about that in a second. What the law of large number says is, over the long run, if you do something a lot, if you run an experiment many times, the observed percentage, let me say this, the observed percentage must match, not must match, but will get closer. It's a probability, the predicted probability. So what I mean by that is, real quick, if you said it was a 50% chance I'm going to flip a head, if I do that 10 times, will I freak out if I don't get exactly 5 heads? No. If I get 8 heads, it's like, who cares? If I do it 80 times and I get 79 heads, will I freak out? Somebody got, all right, I like this. Somebody said no. Happens all the time to me. Like something happening to you. Right? Most of us, I think, would freak out. Number one, you're freaking out that, what the hell's your life like? You're just sitting there flipping a coin anytime. And secondly, that's not what you expect, is it? So probabilities don't make any sense with a single instance. So flipping a coin once, the 50% doesn't mean shit. But what it means is if you did that many, many, many times, then the percentage should come out to that. So if I flipped it 80 times, I should see something close to 40 heads. If I don't, that's evidence that my coin is something messed with the coin. Yes?
I was going to say, back to this thing up here. When you ask somebody, would you like to stay or would you like to switch? Them saying I'd like to stay is a new decision in and of itself, is it not? I mean, he's saying I'd like to stay. That's still a decision, whether you phrase it as, would you like to stay, or would you like to make the choice? I mean, if you had left and come back a year later, I just don't understand the difference. It's just a word difference.
But so the difference, no. Here's the thing. Here's what's behind the scenes. So there's a 1/3 chance. You agree with that? 1/3 chance the prize is behind door number 2. Which means what about the other 2 doors? There's a what chance? 2/3 chance. Is everybody with me? So there's a 1/3 chance it's here from the beginning. And there's a 2/3 chance then it's in one of these 2. Was it in that one? So there's a 2/3 chance it's in this one. So there's twice the probability that it's behind this one. And our brains don't like that. And the reason we have trouble with that is because it's not a mathematical thing anymore, really. Why did I open the 3rd door?
Suspense.
So let me ask you, let's set this up. Ready? All right, 1, 2, 3. You write a number down. Don't let anybody else see it. Just write a number down. One of those, 1, 2, 3. All right. Somebody pick a door.
3.
1.
All right. You guys pick 3. Now, I saw what you wrote down. Right? So I would open up door number 1 and show you that there's a goat. All right. Why did I open up door number 1? There's 2 probabilities. There's 2 possibilities there, right? Either you pick the prize, which happens a third of the time, so I could open up either one of these doors. But if you pick the goat, then the prize would be behind door number 2, and I open this door, right? So I'm restricted in what door I can open. So 1/3 of the time, it doesn't matter which door I open. I'm just going to open up either one. But 2/3 of the time, I have a reason to open up the door I did. Therefore, 2/3 of the time, the prize will be there. Now, what I'm really going to enjoy is watching your reaction when you find out you picked the prize in the beginning. All right? It was behind door number 3. Which doesn't disprove a damn thing. What was the chances you're going to pick the prize? 1/3. Pretty damn good chance, right? If I was a lottery where the winnings was $10 billion and there's a 1/3 chance, Every damn person should play that. Shit. That is good damn chances, right? You with me? I have no idea where the money's coming from. Let me say this again. So, you pick a door. I open a door to show you a goat. Why did I not open that other door? Either I didn't open it just because I just picked one, they were both goats, or the prize is actually behind there. And which one of those happens more often? The prize is actually behind there. That happens 2/3 of the time. Because you would have picked the right door only 1/3 of the time. So should you switch or should you stay? You should switch. Now, the thing that humans have trouble with is that does not mean you'll win if you do that. It means if you did the game many, many times, you would win 2/3 of the time. Right, so in any given time, it's better to switch. Does that make sense? The thing that we just can't understand is that just because, all right, there's a 70% chance I'll make it home faster if I go down this road, and so there's a 30% chance I'm going to go this way. Traffic, what the hell, man? Probability sucks. It's all shit. No, 70% still means there's a chance it ain't going to work. And our brains just don't like that. We like to make everything black and white. Right? The minute it's over 50%, we're like, oh, it's going to happen. Let's go. No, there's only a chance. If you have a 99% chance you're going to survive the surgery, you could not. There's a 1% chance you won't, which is actually 1 out of 100. I actually don't like that, to be honest. 1 out of 100 times that surgery's done, the person didn't make it. I'm like, I know, Doc, improve those odds for me a little bit. Yes.
All right, so I need you to explain this. So you choose 2, and there's a 3rd chance. You open 3, there's a goat, right? And there's a 2/3 chance that it could be between 1 and 3. So if you choose the goat, or if you show me the goat behind 3, then what's the chance of 1? Is it 2/3 that it's behind 1?
So the whole thing is, here, you don't tell me. Don't let me see it. You pick a door that has the prize. You ready? Pick a door that has the prize. All right, you got it? All right, I picked door number 1.
What if I choose the same door?
Huh?
What if I chose the same door?
No. You're the host.
Oh.
I'm the player. You're setting the game up.
Oh, all right.
So whatever door you pick, that's the one with the prize. You right? You with it? All right. So I picked door number 1, and then you say, "I'm going to show you." Now you show me behind which door are you going to show me?
3.
All right. You show me behind 3. There's a goat. And then you say, "All right, Jeff, do you want to switch or stay?" And I say, "I'll switch." So where was the prize?
Well, I mean, you said the goat was behind 3, but...
You said the goat was behind 3.
Oh, sorry. Yeah.
Oh, shit.
Sorry, I got...
But let me see. So if any of you, now think about it. Each of you do this. And then, actually, this is interesting. Let's do this. Everybody, let's try this out. We'll do this because we're going to play this game as many people are in here. I'm the contestant. You're the host. You're going to actually take the goat, and you're going to have, an assistant do it because you're the freaking host. No host is going to be taking the goat. Have them put goat somewhere and pick one of the doors to have the prize. Do it right now. Everybody got a door that has the prize. Does everybody have the door? Everybody with me? What's going on right now? I really want this to work. I can't believe I didn't think about it. This is relatively simple to do. All right, I'm the contestant, right? I say, all right, I'm going to pick door number 2. And then now, let me see. Let me just pick somebody. It doesn't really matter. What? Now you open a door to show me a goat. What door do you want to open and show me a goat? All right. So behind door number 1, there's a goat. Right. So then I switch to door number 3 because I'm thinking. What am I thinking? Why did she show me door number 1? What's most likely? Why did she pick 1? She could have picked 1 or 3. Why didn't she pick 3? Because 2/3 of the time there's going to be the prize behind door number 3, right? So you're almost right in the way you're thinking about it. The door that the host opens is new information for me, the contestant. Oh, it's not there. So it's more likely it's going to be in the other one. Because 2/3 of the time he's not going to choose this one to open because he doesn't know what good with the game. Door number 3 has the prize. Do you want to switch to the other goat? Yeah, that goat was a little sickly. I want to switch over to the other goat. Thanks, man. You guys understand? The door he opens Most of the time, 2/3 of the time, he's going to open a specific door because the other door has the prize. So should you switch? Hell yes. Will you always win if you do that? Hell no. But you'll win 2 times more often as you would otherwise. Any specific instance, I have no idea. Any specific instance, anything could happen. But in the long run, that's the way to go. So it couldn't quite work because I have to have one person that I'm working with, right? Let me see. So I ended up switching to door number 3, I think. How many of you guys had the prize behind door number 1? All right, so I got to figure out how to do this in a larger setting. I got to work on that. But is that semi?
What made most sense for me when I first did the money hall problem is doing it with 3 doors and then doing it with 1,000 doors, and then it was.
Oh yeah. So if you take this to, I was trying to see if I can make it make sense with just 3. But if you do it with 1,000 doors, now watch. So yeah, if you do it with 1,000 doors, let me just draw 1,000 doors real quick. No. All right. Blah, 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 blah. So you pick one, and then the host opens 98 doors to show you goats. He just doesn't open door number 4. He opens up 1, 2, 5, up to 100, and says, "There's goats. Do you want to switch to door number 4?" Well, what do you think? I picked door number 3. There's only one prize. Everybody else has goats. There's 100 freaking doors here, right? I choose door number 3. He opens up everything else except 4. So everything else is open now, except for number 4. Should you switch? Why did he not open door number 4? Probably because it has the prize. What's the chances I picked the prize in the first go? 1 out of 100 chance. So there's a 99% chance the prize is actually behind the door he didn't open. Because why didn't he open it? Because he's got the prize. And that kind of would give away the whole freaking game. What's the point of the show then? Thanks for watching. You probably won't watch next week because there was no drama there at all. Sorry. They're going to ramp the drama up. Of course, nowadays they've changed it because they all know this exists. So now there's like a medium prize and a great prize and a goat. Right? All right. Enough of that. Even if you don't quite get that, there's not going to be a quiz based on the Monty Hall problem, right?
So on Deal or No Deal, should you always switch your thing?
Deal or No Deal. Deal or No Deal has an extra added dimension to it, which is the money that's offered to you. I actually watched this a long time ago. The money that's offered to you is based off of the expectation of what might be left. So then you have to play off the odds to see should I take that or not based on what I think is left. Does that kind of make sense? So there's an extra added dimension to it. But if you think about it, there's like 30 cases, right? So there's only a 1 out of 30 chance you're gonna pick the really big money. So at the end, if there's like $1,000,007 left, I would probably switch. But again, it's not as clear cut as this. Nowhere near as clear cut as this. At that point, it's almost even odds that you got. You picked it. All right, because they didn't give us any. Well, screw. It's not like they're opening it on their own volition. I get to pick which one they want to open, that they're going to open. You with me? So if I say open that case and there's $1 million, oh well, I'm not going to get the big prize, but there's still big money out there. Whereas here, if I picked it and there was a prize, I know everything else is a goat. So I'm just going to go home. I'd rather not get the goat. Pay for gas to get back home. All right.
Pay for a new car.
And of course, poker, you do play odds, but poker has the extra added dimension of human perception and personality, and can you pick up on somebody else's tells? I mean, there's a lot with poker. Poker is not just math, or else I'd be out there playing. I have no poker face, right? I'm like, even though I wear big ass sunglasses and the hoodie, it'll be like, whoa. And you're like, Jeff, really? You're out. Bye. All right. Let me just go home. Play some games. Give me a goat. Could I have a goat?
If you do that for every hand you hit.
Yeah, you're right. If I just do that same reaction, but unfortunately, I'm just not that good of an actor either. Okay, so on page 137, believe it or not, is the law of large numbers that I already discussed. So I appreciate the question that brought us into that. That was awesome. Blah, 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 blah. So let's do this. I like this little problem here to introduce several ideas. If I was going to have 3 kids, not me personally, it's not like a Junior 3 Times Over, one of my favorite Arnold Schwarzenegger movies. If I was going to have my wife have 3 kids, right? What are the different possibilities for the kids that we have? We can have, for example, 3 boys. We could have the first one's a boy and the second 2 are girls, and so forth, right? So what are all the possibilities?
3 boys, 3 girls.
So there could be, all of them are girls. Now let's do this very systematically, and let me introduce the idea of a tree. You don't always have to use a tree, but let's use a tree for right now, just to show you how it's useful. So a tree would say every time you have either a decision or an outcome is possible, you make another branch, right? So here's our first kid. Our first kid could be a boy or it could be a girl, right? So these are the pathways down your life or something, right? Sounds like some really dumb old show. Here's the pathways down your life. Now after the first boy or girl, whatever we had first, we could then have what? Boy or girl. Boy or girl. And then off of those, every time we hit a new thing, and here's a third kid. So I'm going to have another branching. I could have a boy or a girl. Well, what boy? Something would happen to him. Boy, girl, boy, girl, boy, girl, boy, girl. All right. So this top path would be boy, boy, boy. Boy, boy, boy. And then we got boy, boy, girl. And then we got boy, girl, boy, right? And boy, girl, girl. So here's all the ones where the first one is a boy. Okay. And then we're going to just repeat everything again with the girls. So see how it's going to be the same things here, just G, 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 G there. So girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Girl, girl, girl. Right? So why does it make sense that I ended up with as many as I did? How many did I end up with? 2 to the 1. Okay, I like it. 2 to the 3rd. There were 2 choices here. And for every one of those, there were 2 choices there. So that's times 2. Not choice, but you're with me. And then 2 possibilities for there. So 2 times 2 times 2 is 8. That's why this is 8 big. And what is this thing I just created? All right. I've created a sample space, which we normally denote with brackets. So that's what a sample space is. A sample space is a collection of all the possible outcomes. So for an event of 3 kids, all the possible outcomes are listed. Are all of these outcomes equally likely? Roughly. Yes. And in actuality, nature makes the probability of a boy a little bit higher because men, we tend to die sooner. So I love it how nature kind of somehow knows that and gives more boys because we're like, well, there's some boys. Put some boys out there. So the actual probability is like 51% for a boy and 49% for... Let's pretend forever in this class that it's 50-50 just to make it easier. You with me? You guys with me? The real story's not quite that, but we'll go with it. So are these all equally likely? Yes, because if it was all 50-50, then these are all basically the same. If it was 51% for a boy and 49% for a girl, which would be most likely? Boy, 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 right? That would be the most likely. All right, so we'll have to figure out later how to figure it out. But if they are equally likely, and these are, we'll assume they are, if they're equally likely, then probabilities are very simple. If they're not equally likely, oh shit. All right, we got a little bit more work to do. So for example, if equally likely, probabilities are simple. And here's why. If I said, what's the probability I got all 3 girls? What do you think that probability would be? What's your gut tell you? 1 out of 8. There's one event that matches what I want out of 8 possible outcomes, right? So 1, 8. What about the probability that I get exactly 1 boy? So, yeah, you got to be careful. How many of them have exactly one boy? Yeah, I got 1, 2, 3. So this probability would be 3 out of 8.
Oh.
How are we doing so far? Bless you. All right. It's not too bad, right? Okay. So if they're equally likely, probabilities are easy. I'm not always going to give you equally likely events, though, right? So we have to learn in a later section what to do if I have non-equally likely events. Let me make sure I haven't skipped anything. Nope. Okay. Blah, blah, blah. Oh, there's a problem in the homework that everybody always misses. And there's a little section where it says, let's see, was it this one or the other one? Here we go. No, it's not that shit. I guess it was in the other book. But they said, tell me if this is probable, possible, or impossible. Probable, possible, impossible. All right, so it's to categorize these as one of these 3 things. So if I said, I go to a casino and I win on the first 3 pulley-majiggers, you can tell I haven't been to a casino, right? So I win on the first 3, whatever the hell you call them. I just win. I win $1 million on each. Is that probable, possible, or impossible?
Impossible.
So anybody saying impossible, you're wrong. It's not impossible, right? But our brain very often forces things that are very unlikely. We consider them to be impossible, right? But our brain just kind of does that automatically. But we got to realize that just because it's really unlikely does not mean it's impossible. So I would say it's possible, but not probable. So what's the difference between these 2 words? Beautiful, right? This is saying likely, and this is saying unlikely. Unlikely doesn't mean impossible, right? All right. Okay, maybe. So all of you getting an A+ in here is unlikely. But it's not necessarily impossible, right? I don't care how infrequently I've seen it, it's still possible. All right, maybe. Okay. Let's see. Make sure I didn't miss anything out. Nope. So let me ask you this here. Who here is not really familiar at all with a deck of cards? Anybody, like, how many suits are there in a deck of cards? Yeah, there's 4 suits. Let me put it up here. What are the suits? Yeah, hearts, diamonds, spades, and clovers. No, that's Lucky Charms. Clubs. All right, you guys good with me so far? All right, I think most of you should know. I'm not asking you to play No Limit Texas Hold'em with me. I'm just asking, do you know what cards are, what they have in them? How many cards in each suit? What word is that? Each suit has 13 cards. And what cards are they? Let's start with ace low, just because. And then it goes to 1, 2, 3, 10, Jack, Queen, King. I like it. So let me see if I can ask you. And of course, these 2 are, what's true about those 2? They are red, and these 2 are black. Okay, cool. So let me ask you some very basic probability questions. You ready? So even if you don't know cards, here's everything you need to know about them. All right. So, what is the probability? So if I pick 1 card. Good Lord, Jeff. All right. Let's pick one card. It's a probability that I pick an ace. So just to save you from yourself, if you are this way, the first answer for the first one is not 1 out of 4. Do you see where somebody would come up with that answer? Why would somebody come up with the answer 1 out of 4? There's 4 aces, right? An ace of hearts, an ace of diamonds, and they say I'm going to pick one of them. But the basic idea of probability, which you've already used earlier today, is what goes on the bottom of a probability always. The total possible outcomes. So if I pick a card, how many total possible outcomes is there? 52, right? 13 cards in 4 suits. 13 times 4 is 52. All right. So out of 52, how many match what I'm looking for? 4. So that's the correct way to set up a probability. On the bottom goes all the possibilities, right? The total number of things that could have happened. And on the top goes the total number of things that match what I'm looking for. 4 out of 52. Which is 1 out of 13. Which is roughly what percentage? 7.7, am I right? Okay. And real quick, do you see how it reduced? Sometimes when a fraction that represents a probability reduces, it represents another way to look for it. I'll look at it. For every 13 cards, there's how many aces? 1. So every 13 cards has 1 ace. All right, that's nice. So what about the probability of a red card? That should be relatively easy.
What happens?
Yeah, half the deck. So if you do it 26 out of 52, or you can just go straight to, well, half the deck is red. So thankfully, both ways match up. I like it. Anybody in here play poker and actually play it for money? And not just Oreos or something? Nobody? You play poker a little bit? A little bit? So as you're doing this, do you think about like the possible number of outs and stuff like that? No? Or you just kind of go, you know, I'm feeling this one. Right? Which actually could be good. If you have a decent set of ideas in your head, what your feelings are actually based on your own, what you've seen over time. Probabilities. Yeah?
Is that in blackjack?
Blackjack, okay. So I should have restricted to poker. Any card game. Blackjack, of course, they not recently, but a long time ago, they instituted using like multiple decks because they had people that were counting cards, and that's exactly what you're doing. You're saying what cards have already come up, and what's the probability that my card that I want is still in there, right?
I was going to say, yeah, I do some of it like a straight, you know, if you have no kind of straights, like 8 cards in the deck, but you got to figure there's 3 cards used for the flop, and 2 in your hand, so that's 5 away from 52, 47, and you have 8 cards with your straight, so 8 out of 47. So I know
All right. Beautiful. Some of us didn't follow it. What we think about is considering how many cards are already out there. And then you have to think about what are those cards, and then how many cards are left that would help my situation out. Right?
Some of your cards that help you also may also hurt you at the same time, which people don't realize. Like maybe 8 help you, but 2 of them help somebody else.
Exactly. And that's information you can't get until the end. So you try not to think about that. Right? Or you try to read the other player, but I wouldn't even go there because I suck at that too. All right, so what about this one? An ace or an 8?
8 out of 52.
Yeah, I love it, because how many cards am I looking for? There's still a chance. I'm only picking one card. Be very careful. I'm still only picking one card. But I'm okay if I get an ace or an 8. So how many chances do I have to be okay? 8 chances, because there's 4 aces and 4 8s. Stay with me now. Some of you guys are like, this is boring shit, but hold on. I just want to make sure we're all on the same page. So here's a little more interesting question. Let's probably get a jack or a club with a capital C for some reason. How many clubs are there? How many jacks are there? So if you think it's 17 out of 52, you're wrong, but it's thanks for playing. What's the difference here versus there? If I count 4 aces, I haven't counted any 8s yet, so I can count all 4 8s. If I count 4 jacks, one of those jacks is shit, right? So the real formula, what we're actually doing right now, this will be the last thing we'll do. I'm going to let you out early. You guys have been dealing with my horrible handwriting every day, but today I'll just take it into consideration. We're coming up with an equation for the probability of one event or another event. So there's a very specific kind of equation for this. So we realized it would be 4 jacks and 17 clubs, but what adjustment do I have to make? Why do I have to subtract 1? Because that's the one that was both. So if I'd stand up all jacks, the 4 people stand up, and said stand up all clubs, and the 1 jack of clubs is like, I stand higher.
Yeah, you get 13, not 17.
Say again?
Should be 13.
4 plus 13 minus 1.
You need that 13.
Right.
Oh, I'm thinking ahead. Thank you. 4 plus 13. That's 17 minus 1. 16 out of 52, and that reduces to whatever. And you can make a percentage out of it. Cool. So what is here's where we end off then. What is this formula for OR? So the probability of event A or event B. So in this case, event A was getting a jack and event B was getting a club. So what's the general formula for this? Where'd that 4 come from? 4 over 52 was the probability of jack. So for this one, it would be the probability of A. And of course, I added that to the probability of B. Now, now, it's not always going to be -1, is it? It won't always be -1. Because if I said, let me give you one more example here. Probably the king or a face card. Which ones are face cards? These guys. These are the ones that are looking at you, right? Someone with one good eye. Right? So if I said king or face card, well, every freaking king is a face card. So in this case, it would be 4 kings plus 12 face cards minus all 4 of the freaking kings, right? We don't want to count them twice. So don't say it's always 1 there, but what the hell do I put there then in the equation? What's true about that 1 card? It is a jack and there you go, and a club. So this would be minus the probability of A and B. So the word "and" in mathematics has a very specific meaning. It means both of these things have to happen. And the word "or" is either one can happen. In English, it doesn't always exactly mean that. Right?
What do you mean by that last part, though?
So that's one equation. I just ran out of room. Let me do it again, just make sure you guys know. So probably of A or B is probably of A plus probably of B minus probably of A and B.
Alright.
One equation there, right? So why did we not have to subtract anything off when I said ace or 8? Because how many cards are an ace and an 8? In a normal deck of cards, 0. If there is one in your deck of cards, I'm not playing shit with you. No, I'm not going to. All right, that's plenty. I'll let you guys out of here.